this is a video on two-dimensional motion. And this is very similar to one-dimensional motion in kinematics, except now we're going to be dealing with motion that occurs in both the x and the y directions. And I'm going to give you an example. Let's say, for example, you're trying to cross a river. And this is the river here. And all the stuff in the middle is the water. And this is the north bank, and this is the south bank. And you want to go across to the other side. Well, normally if you cross a river and you paddle straight across, you're going to have a current that takes you downstream or upstream. So let's say this river is 100 meters across. So in order to cross the river, you need to move 100 meters in the y direction, right? It doesn't matter what you move in the x direction, as long as you move 100 meters in the y direction, you have successfully crossed the river. You won't end up right here, you'll end up downstream. But let's say that that water is causing an acceleration that, combined with the acceleration of your boat, gives you a net acceleration of 4 meters per second squared at this 30-degree angle. I'm going to say acceleration is 4 meters per second squared. And the question is, how long does it take to cross the river, and how far downstream do you end up? Well, a good way to solve problems like this is to start by making a table of what you know. So, just like we did before, we're going to have variables x in the x direction. We're going to have the, I'm going to make sure I do this in the right order that we did before. Acceleration in the x direction, velocity in the x direction, initial velocity in the x direction, x, and time in the x direction. And then we're also going to have a table of y values, y, a sub y, v sub y, v initial sub y, and time. Now, if there's one thing that you know, is time flows at the same speed no matter which way you're walking. So the one thing that's going to be the same on these two is time. Doesn't matter how you're moving in the x or y direction, time has got to be the same. We have a vector here that's 4 meters per second. So let's find the acceleration in the x and the y direction. If we look at it right here, it's going to have an a sub y. And that a sub y there, I'm going to write it here, a sub y is going to equal 4 meters per second squared times the sine of 30 degrees. So that ends up being 2 meters per second squared is a sub y. A sub x is going to be 4 meters per second squared times the cosine of 30 degrees. And this is a sub x right there. It's an acceleration in the x direction. You do that, you end up getting 3.46 meters per second squared. A sub y. So far about this, we know a sub x is, this is a sub x is 3.46 meters per second squared. A sub y is 2 meters per second squared. We're going to assume that it starts at rest, meaning its initial velocity in both the x direction and the y directions is 0. And then in order to cross the river, it needs to go a total of 100 meters. So this is all that we know right now. you'll notice that we only have two variables right here in the x direction that we know, but in the y direction we have three variables. And knowing three variables, we have enough to find the other two. So what we're going to end up doing is working first with the y direction and finding time. Once we get time, we put it in here. Then we have the three variables we need to solve the x direction motion. So I'm going to erase this picture now to give us enough space. And we're going to find the other variables. Again, you can do this with other methods, but kinematics works pretty well with this sort of problem. So we want to find time in that y direction. And we know that we need to have an equation that has time, but not the y velocity. That velocity. So let's see. Velocity there, velocity there. No velocity in this equation. At squared, sorry. Deleted that accidentally. So let's use this equation right here. And the only difference from this and what's up there is that we're going to change x to y. Because the kinematics equations work in whatever direction we want. So y equals v naught, so y, t, plus 1/2 a to y, t squared. Because we're working in the y direction. We know that y is going to be 100 meters. It starts at 0 meters per second times time. We don't know what the time is, but that's okay because 0 times any number is equal to 0. Plus 1/2 a in the y direction is 2 meters per second squared t squared. This becomes 0. Sort of handy that v naught is equal to 0. If it wasn't, what we'd end up having is a quadratic equation that is a little trickier to solve. You could use a quadratic equation rule. We're not going to really do that in this class. You could actually find this first and then find time afterwards. That works pretty well too. There are different ways to do it. We end up getting t squared is equal to 2 times 100 meters. I'm just doing algebra in my head here. Divided by 2 meters per second squared. So you end up getting t is the square root of, because the 2's cancel out there, and the meters cancel out there, and this 1/2 squared goes up to the numerator, 100 seconds squared, so t is equal to 10 seconds. So we've already answered our question, how long does it take to cross the river? It takes 10 seconds. And we're going to put that in here right now, 10 seconds. So that means when you cross the river, it's 10 seconds later. So now we have three variables, and we can use that to solve for x to figure out how far downstream we are. If you wanted to, you could also solve for v sub y and figure out how fast you're going in the x and the y direction. I'm not going to do that now, just to save time, but you should practice that and make sure you know how to do it. And I even encourage you to work that out on your own right now, or after this video lecture. How far downstream? Well, let's look at this. We now have an acceleration, a velocity, and a time, and we need to find the distance, right? So let's look at these equations here. We have acceleration, velocity, time, initial velocity. We don't have final velocity. Acceleration, initial velocity, time. So we can end up using the same exact equation, right? Let's get the black pen. This time we're working in the x direction. X equals v naught t plus 1/2 a t squared. And those are both in the x direction. So x is equal to 0 times 10 seconds plus 1/2 times your acceleration is 3.46 meters per second squared, times your time squared, 10 seconds. So you end up getting 1/2 3.46 times 100, and the units end up, this seconds once it's squared cancels with that one, so you end up with meters. So let's see, E times 3.46 is equal to 173 meters. So by the time you cross the river, you've got 173 meters. If you ever want to solve for this, you can use pretty much any of the equations. This is a nice easy one, 2ax. If you want to get this, velocity, 173 meters. Might as well finish this off. V squared is equal to V naught squared plus 2ax. So if we're dealing with the x direction, velocity is the square root of 0 plus 2 times 3.46 times 173. Some units in there. So you end up getting 273. Didn't work. 2 times 3.46 times 173. .6 meters per second. .6 meters per second. We want to do this in the y direction. I'm going to change dot. So you end up getting, because the initial velocity is still 0, 0 plus 2 times the acceleration of 2 meters per second squared times your distance of 100 meters. So 2 times 100 should actually work out to be the square root of 400, which should be 20. So V sub y is 20 meters a second. Get this in red, so just to and I'm doing this just to illustrate one last point before we end, is that these are still vector components. So let's say you want to figure out how fast this is moving when it arrives. When you arrive, and you'll find out it's pretty fast, so you better have a good plan to slow down your boat. Well, you know V sub x is 34.6. You know V sub y is 20 meters per second. So at this point, you are just reconstructing or finding the resultant vector here. Using the Pythagorean theorem, you can say r is equal to the square root of 20 squared plus 34.6 squared. I'm going to do that in my calculator right now. 34.6 squared. And I find that it is going at about so that's your speed. If you want to get the velocity, you need a direction. So we can say theta. Well, if the tangent of theta is equal to opposite over adjacent, 20 meters per second divided by 34.6 meters per second, that means theta is just equal to the inverse tangent of 20 divided by 34.6. Put that into your calculator. 34.6. That's 0.58. I need to do the inverse tangent of 0.58. And I get theta is equal to 30 degrees. So it arrives at 40 meters per second at an angle of 30 degrees. It's a good sign that it's at 30 degrees. It should be, because the acceleration was at 30 degrees, so you would assume that the velocity should be too, given that it started at west. This is the end of the first of the 2D motion video tutorials. I'm also going to do a tutorial in a minute on projectile motion, which is a different kind of two-dimensional motion. Thank you.